It's John Black again. I'm just talking here about the twin paradox, which, like I said, is not a paradox. It's just weird, so people call it that. I want you to look over there at the top left. There's a spaceship, and that spaceship is going to the nearest star, which is 4 light years away. Um, Now, the guy on Earth, he's going to look at this. We got a question here. How long did this trip take? Okay. Now we can see it's from the red part, 4 light years, right? He's going 80% the speed of light, 0.8 c. So that means it takes him 5 years. If we're on Earth and we look at him, he will return. I mean, the trip will take him 5 years. He'll return in 10 years. Um, but according to the spaceship frame of reference, right? How does he? Because if he does that, okay, if he does that, if he returns in 10 years, then the speed of light changed for him. It didn't go 186 miles per second. But okay, right? If the time, remember how I said things get shorter when you the faster you go, and they get shorter or contract in the in the path that you're taking, like from front to back. So this distance here is 4 light years for Earth, for the guy on Earth. But for the guy in a spaceship, the universe, and I'm serious, the whole universe contracts. And that distance now for him is 3.4 light years. Now, if he's going at the speed of light, we can see here that it will take him 3 years to get there and 3 years back. It's 6 years for him and his ship. His ship will be 6 years old. He will be 6 years old. Everything about him and his ship thinks that it's 6 years, and it was 6 years for him. Okay. Now, that's how we know that the guy in the spaceship will be younger. Okay. And I want you to think of this now. When his clock is moving, I want you to think, see here, that's a little photon, and these are two mirrors. The photon's going to go back and forth as a clock. Okay, we're going to say, just to do easy math, that when it goes from the bottom to the top, that's 1 second. When it goes from the top to the bottom, it's another second. Okay, 1 second is this line. See there? Now, if you're on Earth and you're looking at your clock, you'll see it go like that. Boop, boop. 1 second, 1 second, 1 second. But the guy in a spaceship, he's going to be moving, right? So by the time, see the length here from here to here is actually, because it's more, you can see that green line is obviously bigger than the blue line. But from here to these two dots is the same length. It's about the halfway point, right? So when you're looking on a spaceship, whatever he would do in a half a second, I mean, it'll only take his speed sped down by half, okay, because it went to the halfway point. And everything about him, you'll see his heartbeat slower. If he throws a ball up, it drops slower. Everything about him is going slower. He's walking slower at half speed. Okay. Now look at this other one. What if he's really going quick? Look how fast he's going here. Now the length of it, it's taking 1/7 or 1/6. He's probably going like 80, 90% the speed of light to get that. So you could see from here to here is 1 second, and you're looking at his clock from Earth. That is 1 second. But when he's inside the spaceship, his clock is 1 second is from here. From top to bottom is 1 second. Light moves the same speed in every frame of reference. From your frame of reference, this is 1 second. But from his frame of reference, it's from here to here. And if you think about it, when he's looking at it, just like you see the light going up and down, but really you're moving. The planet Earth is moving, the whole galaxy is moving. So your light isn't actually going up and down, but you can understand it from your frame of reference. That is 1 second. Even though you're moving, you say you're standing still. Same with a spaceship. He is standing still. He sees his light go up and down, up and down, up and down. So when it gets from here to here, it'll be 1 second for him. If his heart beat 1 second, 1 time per second, he'd get one heartbeat from here to here. Okay. But you on Earth will see that he slowed down by 6 times the amount that you are going. Okay. See how it goes? I want you to look at something. Look at this green line and look at this blue line. Okay. Look at how I drew it over here, right? And look how the blue line is right here, right? And you can do something with this. This is telling you something. And I'm going to have to turn off the video and erase everything and write what it means. But I'm going to get into some math or whatever. But you can see how it forms a right angle. Now, what do those angles and that triangle mean? I want you to look at this over here. See what I'm pointing to up in the right-hand corner there, top? There's your clock. Remember your clock, your photon clock? What's moving, right? You're on Earth, and you're looking at this clock that's on the spaceship. You see the line right here. That's the photon moving. That's what you see. That's the distance the photon moves in your frame of reference. See this red line? That's the distance that the photon moves in the frame of reference of the spaceship. See how it's red, red, blue, blue. Okay, now, if you redraw this into a right triangle, you can see something there. Something's going to tell you something. Something's up. This is c, obviously, is the speed of light. This is velocity, the velocity of the guy in the spaceship. Okay? If you take the speed of light, this distance right here is what you see from Earth, right? And it's a distance. How do we know what the distance is? Because if you take the speed of light times the time it took there, let's say it took a second to get there, and speed of light is 186,000 miles per second, the seconds cancel out, and it gives you distance, right? Same here, distance. Same here, distance. So if you have three distances, you have three lengths. And what's that tell you? Look over here, a squared plus b squared equals c squared. We know that, right? Pythagorean or whatever theorem. So we plug in these into here. See how we plugged them in? CT, CT, VT. Then what we did was we separated them, right? C, because this is c squared and t prime squared. We just wrote it out longer, right? Then we divide by c. All we're doing is manipulating these numbers down just the way we want it. We divide everything by c, both sides. So we get this. Cancel out all the c's, right? Except for here because there was no c, so you leave it in there and divide. Then you take that, minus everything by this big thing right here, which is this. Now you got this formula, right? Now just flip it. Put this on this side and put all this on this side. All you did was flip it there, right? Now this next one, I kind of had to do backwards, okay? But if you notice, this times 1 is this. And this times this is this whole thing. So this equals this, right? All this equals this, which equals that in both equations. So all I did was make it different, right? And we get down to this one. Square root everything. Square root both sides. So you get a t prime. And this one, you can't do it. So you just put it in a square root thing. And flip it all around, right? Take this, divide it by both sides. So you cancel this out. And you got this, right? This is from Earth, your time. What is your time equal compared to his time? That's the ratio. So you might say, well, why can't you in regular life see this happening? Well, let's check it out, man. Let's see here. I wrote it down. Let me see. C is giant. V is small compared to C. Right? It's small, man. So this whole thing here, this fraction, is almost 0, right? So that means if this is almost 0, 1 minus 0 is 1. So this is 1 almost. And the square root of 1 is 1, right? And so, and it's almost 1 because we was a little bit off. T over 1 is basically itself. So T equals prime T pretty much. You know what I mean? If you're just on planet Earth, not moving. But when you get close to the speed of light, okay, let's say you're going exactly the speed of light. Right? If you're going the speed of light, V squared is equal to C squared. So that's a 1. 1 minus 1 is 0. The square root of 0 is infinity. So when you're going the speed of light, you're going your velocity is like infinity. And you could say, well, how are you going infinity? I see light moving at 186 miles per second. But that's at your frame of reference, okay? The light's frame of reference is remember how I said the faster you go, the more the universe contracts or shrinks in the path that you're going. So light photons move at the speed of light, right? They move at an infinite speed because there is no time. Time stops when and the universe contracts to a single like line, a single dimension. So what the light sees is the light comes off of the say the sun and instantaneously is transported across the universe to wherever it hits. You know, it hits your eye or whatever. That is instantaneous to the light photon because there is no time. Time has stopped and the universe has come down into a two-dimensional plane and he just uh, time just stops. To kind of cut the equation off down at the bottom here on the right hand corner, you can see it clearly now, and I wrote it real big right up here. But that last few minutes when I got down to the bottom, it was kind of cut off. Anyways, there it is. And I wanted to say again about how I think about the universe when you're speeding towards something, okay? How I said that it contracts from front to back. Um, I don't know, but I think it's supposed to go down into, the faster you go, it starts out contracting front to back, but then the closer you get to the speed of light, I think everything curves in even on your sides and the universe becomes a single point. But I could be wrong. Maybe the universe just comes together, uh, you know, as a plane, as a two-dimensional plane. Obviously, it's not three-dimensional because there's no time, and there's also one of the three spatial dimensions that people mainly think of is gone because it's contracted all the way into one point um, in that plane. Anyways, this is the end of this video.